This is the difference between, we have been talking about so far about earthquake a lot, but for tall buildings, wind is equally important, sometimes more than the earthquake, depending upon the location and depending upon the height. So as I mentioned before, that these two are very different things, the wind and earthquake. So we talked about this one. This basically is ground motion with a time history. And wind is actually not different, much different from that in reality. In reality, it's also oscillating wind pressure with time. So wind is not constant. When it's blowing, as you can see, it's increasing, decreasing, and the forces on the structure are not actually uniform, and I mean not constantly equal. So they vary up and down, but there is a mean value here somewhere in the middle, which we can take as the average pressure, and then we can apply to the building directly. But the reality is the same form as the earthquake. So now these days, the tendency is that if you want to do just like earthquake, you have seismic earthquake time history simulation analysis. We also have the wind PBD, in which you take the wind pressure in a wind tunnel, and then you measure the pressure at every location on the building on a pressure tap, and then you get the time history of the wind, and then you apply those time histories of the wind onto the structure as a forced time varying force. So in ground motion, we apply just one ground motion for the entire structure, but for the wind, we may be applying like 100 time histories simultaneously, because the pressure is varying, every location, direction is varying. So it becomes very complicated. Second thing is that for the earthquake, the earthquake may last maybe 45 seconds or something, but the wind storm can last an hour or more. So the time history is very long, which means the analysis will take a long time to run. And also there will not be just one, there'll be several wind time histories on the structure at the same time. So people normally don't do that because it's so complicated and so difficult to do. So they take the codes will take the mean. So it reminds you of the equivalent static force from the earthquake. So they take that and apply it as a pressure on this one. So that's the basic concept. But the wind people are saying, no, that's not good enough. You should also do the same thing as with that. So that brings us back to our equations. Where does it fit now? Where does earthquake? So far we have talked about two groups of equations. We have talked about this group, and we have talked about that group, and we have talked about left group and right group. This is nonlinear, this is linear, this is earthquake, this is force vibration. So wind belongs here and here in reality, but we normally bring it to that level for the analysis. We just convert that into equivalent force and just apply it. So it really belongs here, truly. It's a time varying force, varying with time, and then mass acceleration, damping, and everything, and nonlinearity should come into play. But normally we ignore nonlinearity for wind. We design it for service. We come to this level, and even that is too difficult, so we go to that level. So that's how inaccurate or approximate the wind code analysis really is for structures. We are very far from the true behavior. And there are things like structure-wind interaction, aeroelastic effects, and many things which are even beyond this one. So that's the reality. For very tall buildings, very flexible buildings, people have to do all those things. Okay? The codes, as I've said, do something like that, that goal thing. So this could be like 10 minutes to hours, this one. Okay, so that's so wind and earthquake. Now we have the comparison side by side. Nature of loading: sustained, fluctuating, repeats daily, impulsive, transient, rare event, duration hours and seconds to minutes, and frequency, low frequency, narrow band, broad band, rich content, because as you can see from that one. And then governing limit is serviceability. Here it is life safety, strength, ductility, response time elastic, response time inelastic. So you can see these two are quite opposite to each other. And this is a problem in the design, because you're taking the same structure, same kind of loading, and then following completely different rules. So you can't add apples and oranges together. So people are saying it's not right. You have to unify them And that's why the wind PBD and seismic PBD are now on similar ground. So you can have, apples to apple comparison of the two kinds of forces, right? Okay, so that's the background behind that. Coming back to the wind, we have a long wind and a crosswind. So when the wind is blowing on a building, there is a force which is along the building, and there is a force which is across the building, and there is a torsion coming onto the building on the plan. So you get three immediate effects. Something structure bends along the wind, and then it moves across the wind and also can twist. And so those three things have to be considered at the same time. And it twists because of the vortex shedding, which I'm sure you all know what that is, because when the wind goes around, it gets disturbed and it starts moving left and right and pulls the structure because the pressure varies, the vacuum is created. So building goes to the vacuum, comes back, then pushes again. So you have very high dynamic effects of crosswind, even though the wind is flowing along and it's constantly flowing. So constant wind can produce vortex shedding, and then you can see here, this wind also, the pressure from this side, it increases with height. So so there are complications in terms of the direction along and across, number one, vortex shedding, number two, and then varying with height, number three. All of this combined together puts very irregular forces onto the building in all directions and height along. So that means the building gets a lot of wind, a lot of forces in different directions, different locations at the same time. So this is the reality of the wind. So the codes try to capture all of that, and this is similar to UBC 97 earthquake I showed you. They try to reduce the whole seismic thing into one simple equation. V is equal to omega something W. This is exactly the same concept, that reduce all the complexities that I mentioned into one simple equation by factors. So that's the code. So we have wind velocity, wind speed factor, we have the pressure, then we have the design wind, and then design force. And from converting from here to here to here, there are formulas and factors and factors and factors. I'm not going into too much detail of this one, because when we do it they talk about how to implement in ETABS, you can see these formulas. But basically, you can see we have a velocity pressure coefficient, height dependent, topographic factor, depending upon where the building is, because the terrain will affect the wind flow. So if the terrain is hilly or plain or other buildings are there, then the effects are different, especially if other buildings are there. Then wind direction factor, then gust factor, because of the dynamic effects, and then external pressure coefficient, which is each face of the building will have different pressure, because as I mentioned, there's a windward side, there's a leeward side, and there are the other sides. So each side gets different pressure for the same wind based on the local wind pressure coefficients. So you have many things to combine together. Same wind, many pressures on different sides and many pressures on different height. So normally it takes a lot of time, lot of effort to do these calculations, especially for a low-rise small building like a warehouse or a pitched roof house. Very complicated because of the angles of the roof and the directions of the roof. The whole thing becomes very complicated. It takes hours and hours just to calculate wind pressures. And this is more normally now in a building, ETABS can do that automatically because it knows the building size, but then you have to define a diaphragm so it can calculate the size of the building at each floor. So it tries to do those things automatically. But codes methods are not enough. When we have unusual shapes of the building is not regular, complicated architectural building, then this doesn't work. Also, greater than 200-meter height doesn't work. These are not designed for buildings greater than 200-meter height. So when the building is greater than 200 meters, then you need to put it in the wind tunnel test. Then we have the long wind and a crosswind pressure. I told you the problem. This is something that most engineers, especially who are not designing tall buildings, do not recognize this problem, because for low-rise building, it's not a major issue. Low-rise buildings are generally designed for a long wind pressure, because the crosswind oscillation, they are not, I should say, soft enough to respond to that one. Because this happens on normally at low wind speeds. So it's not a high wind, not a storm. It's a normal low wind speed, and it's just flowing, and it starts to create these crosswind, eddies, and then the building starts to move slowly, and then it starts to resonate, and then it starts to move more and more, and sometimes it just collapses. So that's the reason we do the wind tunnel, especially. So a long wind is easy, core treatment is there, and it's good for low-rise buildings. And for most buildings, a long wind is larger response for squat, stocky, short buildings. Tall buildings, not so. Often the governing response is a crosswind. And this is because it's a new concept, or it's a different concept, not new. Different because it's not related to wind direction. So people don't really understand why my wind is this direction and the building is moving in the other direction, and I have to design for that first. So it's like this, if the wind is flowing like this and building is moving in that direction. You will expect that the wind is going this way, building should move like this, but no, it moves more on that direction. So that is the reason that and wind tunnel tests are able to detect that. And small changes in the building form can prevent the vortex shedding. Just adding some spoilers, some openings, and there's a famous saying by one wind design engineer that you have to confuse the wind. So don't let the wind flow smoothly. We normally think that building should be smooth. That's not the case. It's not good. Because smooth, like a wing, aircraft wing, is very nice, but it lifts the aircraft so much, force is generated across the wing, that aircraft is lifted up. You don't want that on your building. That wind is flowing this direction and building is subjected to large pressure perpendicular to that, the building starts to, collapse. It's exactly the wing placed like this. Imagine an aircraft wing like this, wind going like this, and the wing, so much pressure on it that it lifts off the plane, right? So that's what we want to avoid. We don't want a smooth aerodynamic shape of that kind. Different kind of aerodynamics is needed. So then comes damping, because damping is, as you know, is important when we have dynamics, and then when we have crosswind, it's purely dynamic response. So now damping becomes very important because now the structure is moving just like it's moving in earthquake. So that means now you have the same mass acceleration damping velocity relationship. So which means that if you now want to control, we need to put the damping there. And damping is more effective for wind than it's earthquake. Also earthquake, but wind is more effective. So you put the dampers to restrain the movement. So we use the damping, steel frame. We use even lower damping for wind than earthquake. And that is why do we use lower damping for wind than for earthquake? So, right. So for earthquake, immediately first 2-3 shocks, cracks will develop, and then the damping will increase. But wind is not like that. Wind is normally uncracked. So the original damping, fresh damping, is still present, and we can't make a mistake on damping. So damping is very critical for wind response. So that's why it has to be determined accurately. Normally for many structures, the actual response is determined after the structure is constructed, and dampers are installed after that, not during the design. So dampers are designed once the structure is complete. So they get the real damping properties of the structure and then adjust things. Okay, so supplemental damping system, tune match dampers, you all know about that, viscous dampers, tune liquid dampers. I'm sure you will read and study a lot. And the important thing is that damping has a relationship with the natural frequency, or so the peak acceleration, which Mark also mentioned, is the primary criteria for wind design. It's not so much, of course, strength and serviceability and all is important, easy to do. The difficult part is always going to be in a tall building, making sure that your accelerations are within limit. Very, very challenging to do. Many buildings do not automatically qualify, especially tall ones. And the engineers get stuck with the design for acceleration control, not for strength, not for ductility, but acceleration. And strength and ductility are almost never tested, but acceleration is daily tested. So if you make a mistake on acceleration, people will start complaining right away. So that has to be done very, very reliably. That's why wind tunnel tests are very important. So then finding the right damping to make sure that the acceleration is correct. So those are the limits. And so this is the damping effect. As you can see here, that with increased damping, you can bring this response down a lot. So the idea is to avoid the resonance effect. The wind oscillation with your natural period is the swing effect I told you before. So if your swing is going like this and the wind is also exactly the same frequency, then your amplitude of the swing will increase and then it will be unbearable. So that's why wind design for the tall building, especially more than 200 meters, is very critical. It's not about high, strong winds. It's about even low winds, normal winds. Right? So and those are the limits. Mark also mentioned that for different office buildings and hotel buildings, you have different limits and normally very difficult to achieve. So dampers are normally required to do this one, and dampers are expensive, millions of dollars. So that's why it's important that the building design is done with due care. First of all, building form, building edges, openings, these kind of things are done first to reduce the effects. And if that doesn't work, then you add dampers. All right, so we have this slide, and I want to explain this one, and I'm sure you will get a chance to visit the lab and talk more about it. But the thing is that we are interested in three things when we look at the wind analysis for tall buildings. One is that we are interested in the overall response of the building. We are not interested in the pressure distribution. And we calculate this is the model, which is the first one, the high frequency force balance. So this model will be placed in the wind tunnel, and this is very rigid and no mass, or almost massless, and stiffness is very large, and mass is, if you carry it, you will feel that it's very, very light. It's made from balsa or now 3D printed foam. Very light. That means stiffness is extremely high, mass is very low, because we do not want any contribution from the natural vibration of the structure. We want this to be completely rigid so that we can measure the forces at the base. So that means when the wind is coming, the moment and the force at the base are measured, and they are back converted into pressure from there. And then we compare it to the code. But we do not want the structure we don't care about the pressure distribution here. We also don't care about the interaction between wind and the structure. So normally this will be rotated. In the wind tunnel, wind will be blowing like this. So every angle, every 10-degree rotation, moment and forces at the base will be recorded by load balancing at the base. So we will get complete force, moment and force profile for this one for every angle of rotation. And this will be used for structural load calculations overall. Then this is a second model. This is the high frequency pressure integration. So this one, if you look inside, you will see that there are hundreds of pressure taps. If you look closely, there are small holes on the model. And each hole is wired to this type tap, and this will go down, and they will be connected to, these are tubes actually, very small tubes. And then the pressure will be measured at every location on the surface, and especially at this location, because this is very important, pedestrian wind comfort. Because normally when you make tall buildings, many tall buildings, the wind goes very fast between the buildings, and it causes a problem for the pedestrians. So pedestrian comfort becomes very, very critical in buildings of this kind. So we need to measure the pressure close to the ground on the top of the building around this one. And this is not alone. All the buildings around the building also need to be modeled. So we can follow the wind pressure, built up suction and all of that stuff. So this is used for design of the cladding because the glass should be designed locally for each pressure. So then this pressure at each location will be used to design the cladding and the glass. And this will be used to design the pedestrian comfort and pedestrian flow. So these two are separate models. This is more expensive. This is, of course, cheaper. And this can also be used for time history analysis. So each wind tap, each cell will have the pressure plot over the 2 hour, 1 hour wind, and then that plot will be a time history, and it's saved as a separate data. So then you can bring it back and then apply them as point load at each location attached to the forced time varying force, and then run the whole thing. So that's the way typically. The third one is aeroelastic. Normally structures, we don't use aeroelastic. This is when the structure and wind start to interact, because then the movement of the structure is so flexible that its deflection changes its shape so much so that it will change the wind variation on the structure. So that's aeroelastic. Normally, we don't do aeroelastic except for bridges and maybe for very slender towers. Now, the good thing is that we have 3D printers that do this. Before, it was made by hand. So normally, it will take 1 month for a craftsman to make a model. So the biggest problem was making the models. And it used to take a lot of time using balsa wood. And then every detail has to be made, so time consuming. And then, of course, 3D printing came, so now you can just print it. And this is printed in pieces and then assembled together. It's not one printed one. So each section is printed and then pieced together, because you have to put the cables inside, so it cannot be one piece. And big companies, they have very large printers, extruders. So they just pull the building out from this one. So very high, large, tall buildings like Burj Khalifa, they need a very big model in the scale. So they are normally just extruded. We have an extrusion printer in the lounge also, small one, but it's also extrusion. It's not printing like this. It's just liquid. You just pull the thing out from there. So that's very high quality or high density material you can print.